Greetings and welcome to another VMBlock screencast. In this screencast we're going to continue our learning of the Rust programming language using this book. Now, so far in the previous video I've covered chapter 1 and chapter 2. So we've got an introduction into Rust, how to install it, how to run a Hello World program, how to use cargo, and we've programmed a basic guessing game. So we've got a good grounding into Rust at this point. Now what I wanted to do actually in this video is jump right over to chapter 12 here, where we're going to build this IO program where we're basically going to implement a very basic version of grep. And in this video, I'm assuming, or at least I recommend, that you, if you want to follow along with this as a beginner of Rust, that you actually have already read chapters 1 through to 11 of this book. I haven't created videos on any of the other chapters. I did record a lot of the stuff, but I decided not to publish it, and I think it's better that you just follow these chapters yourself and then come back to this video and we'll run through this particular section together. So without further ado, let's jump right into the video and enjoy. Thank you. So in this final section of the Rust programming course that I'm following here, we're going to look at how to build a project that is a command line tool. It's basically going to be a copy of the grep command line tool utility. It's going to be based on that, but also if you want to look at a full implementation of grep in Rust, then you can check out this RIP grep, however it's pronounced. And that will give you an understanding of how to implement a full-featured grep tool using Rust. But in this chapter, we're going to go through our own basic implementation using the knowledge that we've gained through the previous chapters of this course here. Namely, we're going to look at organizing code, using vectors and strings, how to handle errors, using traits and lifetimes where we need to, and of course, writing tests. Moreover, we're going to introduce some of the concepts that we haven't covered yet in future chapters, such as closures, iterators, and trait objects. Now, for me personally, I'm going to conclude at this chapter here, and I'm going to do this project, and then I'm going to move on to learning how to implement Rust using WASM in WebAssembly. And that will be a brief interlude before I go into CosmWasm and using Rust for smart contracts. I'm going to use this book as a reference as I journey through understanding and building smart contracts in Rust. But as I mentioned earlier, my primary reason for learning Rust at this point is to be able to audit Rust-based smart contracts so that I can check and identify security vulnerabilities before they go to production. So having a solid core foundational understanding of Rust is a good stepping stone for me to move forward. That's why I will stop at this chapter 12, but I'm sure at some point in the future I'm going to want to dive into understand closures, smart pointers, concurrency using threads, some of the object-oriented features, as well as pattern matching and these advanced features here. But I think for me, for now, this is probably enough for me to jump over to the next step of my learning. So anyway, let's continue with this project and see what we get out of this. This should be quite interesting. So what we got here is the first step. So we're going to create a new project using cargo new, and we're going to call this mini grep. So let's get started and run this command in our terminal. Okay, so the first thing to do is to understand the interface requirements for our application. And really what we want to do, if you think about grep, in its simplest form, we need to tell grep what is the file that we want to search and what is the string that we want to search in that file. And so in order to use cargo, we can use the double dash syntax, or 2 hyphens, to indicate that the following arguments after the 2 hyphens are for the program that we are running rather than cargo. So basically something like this. So this here would mean that we want to run our Rust program, and we want to pass in these two parameters, the first parameter being the search string and the second parameter being the file that we want to search in. Now, there are some libraries that exist and that are available in crates.io that will read and process arguments to an application, which is not unsurprising really. But because we are learning the journey for learning Rust, we're going to implement this ourselves so that we understand some of the libraries and some of the approaches that we would use to do this. So let's take a look. Okay, to read arguments in our application without using a library imported from Cargo, we'll need to use the standard libraries std, env, args function. So the way that we do this is we bring this in using the use statement, and then we can call it like this. And we then call collect directly on this, and collect is essentially an iterator that will produce a series of values. And so we can turn that into a collection, and in this case it will be a collection of a vector collection of strings. So remember, vectors are a bit like arrays, they're just dynamically sizable, and this is using generics, so we're just saying give me an array of, or a vector of strings based on the return of this collection. And env args will basically wait, or not wait, but parse the arguments sent to the command in the terminal. Now here we got this debug or dbg macro, which will print out the arguments that we, or print out this variable here that we pass it. So obviously this argument here, this variable, is going to be this vector of the args parsed from the command line. So let's copy this into our application, and let's try to run this now with cargo run, and then dash and then foo bar, and we should see foo bar output. So actually what we do see are the arguments, which is this variable, so we get the name of the variable, and then the contents of this variable, which is this vector of strings. Now we do get the foo bar, which I typed in here, but we also get the name of the executable, which is just useful for debugging purposes, so we know exactly what we're looking at here. So that's the first step into our application in order to read the arguments. So now that we are parsing the command line arguments in our Rust application, we need to then save the specific arguments that we're interested in into local variables. So the way that we can do that is to use this approach where we've already got the arguments, and we know that the first element of this arguments vector contains the name of the program. And so therefore we start at index 1 here and index 2 for the query and the file path accordingly. So let's copy this in and run this, and we can do cargo run, and in this case we want, let's say we want to search foo in bar.txt, and as we can see we get the output searching for foo in file bar.txt. So that's great, it's working. Okay, the next thing we want to do is read a file. So what we've got here is a copy of a poem, so we just put the poem text into a file and save this in our root. So I've done that already over here, got the poem text file in the root of my project. Now I'm going to update the code in the sense that I'm going to add these two lines here to my main function. So I'm going to put that here and here, and I'm also going to use stdfs. So I just put this here and replace this with fs. Okay, cool. Now let's take a look at this. So what this does is, obviously we're using this module, the file system module from the standard library, and we're calling the read to string function on the file system module, passing in the file path that we include in our parsed arguments. And this returns the handle essentially to the file, and we just use this println macro to output the contents of the file. This is really, at this point, just a sanity check. So let's run the function again. Let's run this program again, but this time we want to pass in the actual file name, which is poem.txt, and hopefully we get the output of the poem, and we do. So there's no searching going on at the moment, but what we've got are the two things that we really have done so far, which is to read the arguments, store them into a couple of variables, and then use one of them to open the poem file that we specified and return the contents of that file. Next up, we're going to refactor the code. So in this section, we're really doing some refactoring to improve modularity and error handling. These are all best practices that you want to follow for most programming languages and most programs that you write, and Rust is obviously no exception to the rule. And as programs get longer and longer, you need to make sure that they are well organized, modularized, and have good approaches to naming conventions, function definitions, testing, and so on and so forth. Now in this section, we're going to address 4 specific problems. The first one is the fact that main now has a responsibility that is growing, and it takes on multiple responsibilities, and really main should be as simple as possible, and the responsibilities for different areas of the application should be in different functions and or different modules. So in this case, main currently performs 2 tasks. It passes the arguments and reads the file. So we want to separate these concerns. The second problem is about the query and the file path configuration variables are inside the main function. And so again, we want to keep these types of configuration variables inside a variable and a configuration structure. The third problem is about how we use expect and how we're not producing a human readable, or let's say useful, error message to the user. And finally, we are using expect repeatedly throughout the code to handle different errors. And so if the user runs a program without specifying enough arguments, they will get an index out of bounds error that doesn't really clearly explain the problem. So it's not user friendly. So let's address all of these concerns, and we'll start with the separation of concerns for binary projects. So essentially, the separation of concerns for binary projects really revolves around cleaning up and simplifying the main function of your Rust program. The idea is that the main function simply should be the entry and exit point of your program. Everything else really should go inside your modules, which should go inside lib. So essentially, you start off with the main function in the main RS file, and very quickly it's going to get too big. It won't take too long for that to happen. So at that point, you want to extract out everything except a few things that remain in the main function. And as I said, the way to think about it really is that main is your entry and exit point for your application. So what you probably want to keep in main are what's mentioned here. So calling any command line parsing logic, that would be a call into the library code that will do the parsing. Any setting up of configuration can remain in the main function. Calling a run function on lib. So basically the user calls main and then main calls run. Finally, you want an exit. So either the exit is through an error, which gets handled and then returned, or simply an exit that might say bye-bye or just exits gracefully. So this is a standard pattern that's followed with any similar types of languages that use a main function as their entry and exit point, as Rust does. Okay, so the first thing we're going to do is extract the argument parser. So if you wanted to do this step by step, the first thing you could do, and the sort of easiest thing if you like, is to extract that logic out to a separate function, but keep that function still in the main RS file. So as we can see here, we've called a new function called parseConfig that takes the args. Now notice that we're using the ampersand here, which means we are lending the variable to the calling function here, or to the function that's being called, I should say, which means that it gets a reference to this variable. This means that it's not moved, it's just referenced into this function here, and therefore it doesn't go out of scope in here. And what do? Well, we've basically made the parameter args of type string array, and you can see that so it's not basically passing in a vector string, it's passing in a string array. And notice that it also returns references back to the substring type that can then be used to set the query in the file path. So it returns a tuple basically as to these two variables that's been passed from the arguments. Now of course the function itself is pretty straightforward, but again this is all about separation of concerns. So let's run this, make sure that this works. So I'm going to copy the function definition in here. So it's still in the main RS file, and I've just copied in this function. And instead of running the code in here, so I'll just remove that, and I'm going to call parseConfig instead. And I'm going to set query and file path in main like this. So parseConfig, and I pass in a reference to the args variable, like so. Now this is going to return a tuple, so I need to wrap this in parenthesis, like so. Okay, actually let's just delete that. So I think that's going to work, but let's ask Rust compiler. So we'll run, and I'll run it with foo poem again. Alright, cool. That seems to have worked still. So the refactoring is working, and we can move on. Okay, let's refactor this a little bit further, and in this case what we're going to do is properly convey the meaning of the config that we're working with. And the way that we can do this typically, and the way we're doing it here, is to use a struct. And so what we can do is we can implement a struct like so that has query and file path, and we update the parseConfig function to return that struct. Now one thing you notice is different here is that we're calling clone on the args that we pass in. And this is because we want the struct that returns to own the data here, the query and the file path fields. And the only way, but the easiest way to do this at this point is to use clone, but it can be a bit less efficient than using a reference. But for now, it's easier and cleaner just to use this approach. So what I can do is I can copy this code into my local function here, my local version of this, and we can just take a look, make sure it works as expected. So we're calling parseConfig, and I think that doesn't change. We're still passing in the arguments in the same way as a reference here, but we're returning config, so that means we need to change the return type to config. And then it means that the way that we access query and file path now comes from config. So it'd be config dot query. So this would be config dot query and config dot file path. Okay, let's see what happens if we run this. Okay, and it's working fine. So the refactoring seems to have worked. Refactoring further still, we can make the code more idiomatic by adding a function or a method to the config struct that actually creates the config. This is because when we are actually calling the function earlier, the function to create or parse the config, this calls another function which returns the config. So the refactoring is essentially to add a function called new to the config struct that does exactly that. So let's try that in our code. So I'm going to copy and paste this in my code here, and I'm going to refactor this. I'm going to replace this to be config new instead, and we can try to run this. We'll just run cargo run, and it works. So just to clarify, we've, instead of calling a function, we have defined a method on the config struct called new that takes arguments that we've parsed from the CLI, and this is defined here as an implementation on the config struct. The new function works in the same way as we had already defined it. It takes in the string array, returns an instance of the config that it's building, and it does this by cloning the first and the second index of the arguments and returning them as query and file path attributes of the newly created config. We consume that here, and then we work with it in the same way. So now let's fix the error handling. So if I try to run the program in a way that will cause an error, for example, if I don't pass any parameters to this, I'm going to get index out of bounds error. The len is 1, but the index is 1. So this isn't really user-friendly at all. So how can we improve this? So the way to best handle errors in Rust is to use the result object that we can return from the function. So in this case, I'm going to update the build function. Actually, we're going to rename the build, rename this from new to build. This is just a standard so that anyone who's using your library will expect perhaps there might be some errors, whereas or some panics. But with a new function, generally that it isn't expected. So with a build function, we could have an error state. And so what we're doing is we change this to build, and we change the return type to result. And the result, if you remember, has two options. It either returns the OK option, which in this case will be the config itself, or it will return an error state, which in this case is a string type, which will be have a static lifetime throughout the program. So in other words, this just returns the error string. Then what we do is we add this condition at the top to detect if there could be an error. In other words, if the length of the arguments is less than 3, then we know that there is not enough arguments passed in by the user. And in this case, it will return the error type. Now, because the return type is this result, it's going to fill in this part with the string, and the config will remain unset. Now, the rest is that if this works okay, then it's going to extract out the query and the file path as before. But the last line is slightly different because it's going to wrap the result, the resulting config, in an OK statement so that it again fits with the interface of this result call here. So I'm going to copy this into our function, or into my code, I should say. So I'm going to go down here. As you can see, I've still got the new function here, so we're going to replace that with build. And we need to update this here as well, but there's a lot more that we can do here, because now in main, when we call this, we can actually do a lot more with this. We can actually react to this in some way. So let's just go back to the docs and scroll down, and let's copy and paste this line and just run through what this is doing here. So basically, we're able now to call build, which remember is this method here that's defined on the config struct, and we pass in the arguments as before. But now what we can do is call unwrap or else. Basically what this means is if there is no error, then it will set the OK part, which is this part, to the resulting config that's been built. And in this case, it will unwrap because it returned OK. So the unwrap part of the unwrap or else call here will execute, and it will unwrap the OK with the config, and the rest of the program will run. If there is an error, then it will go into this else section, which runs this part here. This part here is actually a closure. It's an anonymous function here, essentially, between these two braces. And you can think of this as code that is like a function that doesn't have a name. Basically it's a block of code that can be passed into another closure function. So it's part of this else section here of this function here. And what this does is it passes in the error string that is returned from this. So it would be the error string here that's sent back through this section here as a static string, and it will output problem parsing arguments with this string, and then it will call process exit 1. So that is the exit error for your application. So let's try that again, and we actually get an error here. It's related to mismatch types. All right. Okay, so the mismatch types was because I forgot to use this statement here, because we're using this new library module to deal with the exit code. But with that change afoot, it now runs as expected. So you can see here I didn't pass enough arguments, so it goes into the else section because the build returned the error string. If I, on the other hand, do pass enough arguments, it should behave as normal. Great. Okay, the next refactoring is basically to define a run function which main passes over the logic control to. Remember that main should be treated as an entry and exit point essentially in your program, and so the middle part where you run the actual logic and perform the actions of the application, you want to hand that over to a library typically, and so you would call a function called run. So what we're doing here in this example is we've defined a new function called run, and we're calling it by passing in the config. So over here in my code, I'm going to just drop that function in, the run function. Notice it's exactly the same as what we've got here, so I just replace this with run and then config, and then we can run this and everything should still be good. So like we did with the build method earlier, we can also return the errors from calling run back to the main function that called it. And this allows us to more gracefully and more elegantly handle errors in our application. So if you take a look at this code snippet here, the run function has been refactored in multiple ways. So instead of returning nothing now, it returns a result. And the result is either going to be, remember, OK or error. And in this case, the OK portion is empty, as the run function doesn't actually explicitly return anything. And the error part is going to be this dynamic error, essentially. Now, in order to make this work, we need to include this package at the top here, this module. So that's the first thing that we've done, is change the return type. Now the second thing that we've done is, instead of calling expect on the read to string function here, we just add this question mark. And this question mark will return the result or the error, and that can then be used as part of this return type here from the call to run. So this allows the caller to handle the error rather than the error being handled in here. Of course, it allows the caller to do what they need to do with the error in terms of handling it, displaying it, moving away from it, whatever it is that they need to do. Because you can consider this to be more of a library function, this run function here, rather than part of your core application. So that's why we're allowing the caller to handle the error themselves. And the last change is essentially that we're returning OK with this empty parenthesis here, meaning that it's the same as before. It doesn't return anything, but if it's OK, we need to indicate that it's returning OK and that there wasn't an error. So they're the main changes that we've made. So let's put that into our code. Okay, like that. And I need to also add the errors library. So it's std errors error. Errors error. Like so. And then I can run this cargo build. Okay. And there was something wrong there. That's just error. std error. Let me try that again. Okay, and it seems to have worked, although there is a warning, unused result that might be used. This result might be an error variant which should be handled. So yeah, what this is saying is, if we go back here, saying that we should handle the error, because remember, one of the reasons for this refactoring was to allow the caller to manage the error in a way that they want to. So let's do that now. And so from the docs, the way to do this is to use the if-let syntax like this. So let me copy this in and make sure that this works and it doesn't break anything, and also it removes the warning. So let's clear that out and run the command again, and it works without any warnings or any errors. Let's just check actually that the errors are still getting caught. So let's run this without any parameters. And there we go. Cool. So this is now calling run with the config. Remember, the config is being built up here via the struct. The run method takes the config and returns a result. If the read to string has an error, it will return that. And if there is no error, it will return the actual, or it will print out the contents of the file and then return OK, which will exit gracefully. Now, one thing I didn't check here is that there will be an error if the file is missing. So let's try that. If we do this, it's giving us an error from the config, if you remember, not from the run function. Right? So let's try causing this to error, which would cause this question mark to return the error, which would bubble up to here, and we should see application error this time. We get the application error by just passing in a file that doesn't exist. And sure enough, we do get that. Notice that it says application error, no such file or directory, OS error 2. Nice. So it's working. Okay, so what I've done here is I've done the last little bit of refactoring, at least in this section, which is to move out all of the logic from main RS into lib RS. Well, not all of the logic, but just the logic that shouldn't be in the main function. So the main function still reads the environment args and collects them into a vector of strings. It still calls build on the config struct, and it still tells us what it's going to do, essentially, and then it passes that config to run. It also handles the errors, right? So the main function still deals with conditions where the build has an error or calling run has an error. But apart from that, all of the logic essentially for building and running the application is now in this library. And so the library is familiar because it's containing the same code we saw previously in the main RS, The main differences are actually that we've had to annotate everything with public for now. So everything is publicly exposed in this library that we can use from here. In fact, this is one of the reasons why we have to prefix it with the namespace of the application, which is mini-grep. So now when we call config, we have to say mini-grep config build and mini-grep run. But other than that, the config struct is the same, the config build is the same as we've developed, and the run is the same. So now we've got our separation of concerns, we're handling errors better, we're separating what the main function does with the library, so it makes it a lot easier for testing. We can confirm this works by running the application again, and as you can see, it's output the poem as expected. Moreover, the error handling still works as expected. If I type in a file that doesn't exist, or I don't pass in enough arguments, we get the appropriate errors. Okay, so we're going to test our application now, and we're going to follow TDD, test-driven development. Basically that means that we write a test that fails, and then we write enough code to make the test pass, and then we refactor and keep repeating until we are satisfied with the code. So here's the test. The test is pretty straightforward. It will be dropped into the source librs, and remember we had this annotation here to specify that we only want to compile this when we're running the tests, and we use this to bring in all of the modules of its parents. So this would be everything else that's outside of the tests will be brought in so we can use them and test them. Then we annotate the function with this test attribute, and we start the test. Now the test itself is simply where we create two parameters, query and contents. The query has a string, duct, and the contents has a multi-line string, which is this content here. Now, following that, we have this assert statement, which is assert macro, and we create a vector using the vector macro, like so, and we call the search function with the query here and the contents here. So what this is essentially saying is we expect this function to return this vector, which is safe, fast and productive, when we call the search function with this query and this contents. So in other words, it's going to find this line because duct is here. Alright, so what we need to do in order to get this to at least compile is to provide the interface of the search function in the library file. So let's do that. I'm going to just paste that in right underneath run for now. And I'm going to come back here and I'm going to run cargo test and see what happens. Let's scroll up here. As expected, the test fails. It says the left side doesn't equal the right side. The left side of the test equals safe, fast, productive. The right side, which is the call to search, is an empty array or an empty vector. And it's not surprising it's an empty vector because there's no implementation yet. So let's fill in the implementation of the search function to eventually get the test to pass. So in order to write the code that will pass this test, we need to do the following steps. We need to iterate through each line of the contents that are passed in. We need to check whether the line contains the query string. If it does, we add it to the list of values that we're returning. If it doesn't, continue, and then we return the list of results that match. So essentially this is the solution to the search function. So we can copy and paste that over to our code here. So instead of returning an empty vector, let's return the results. Now the way this works is we create a new mutatable vector that will hold the results, and then we take the contents that are passed in here and call lines, which returns an iterable object of lines. That's how we can use this for loop. So for each line in this content lines, we then jump in and check, does it contain the query string? If it does, then we're going to push that line to a results vector. Otherwise, we'll just continue to loop around until we're done. Once we're done, we return the results vector. So let's run the test and see if that passes. And it does. Awesome. Cool. So given that the tests are now passing, this means that the search function in the library module of our application is working. So now all that remains is to use that in our run function. So we're going to update the run function such that it does what we see here. So where's the run function? Okay. So at the moment, the run function just loads the contents and doesn't do anything. Not very useful. Now all we do is the same thing, we load the contents, but this time we can use the config query to get the search results by passing it into the search function. So notice essentially what we're doing here is we're calling search and then looping through all the lines in the search result. Remember that it returns a vector, so we can basically loop through all the lines in that vector, or all the elements in the vector, and print out the line. So this is the moment of truth. We should be able to run this now using our real life poem that we've got. So let's run this, and instead of foo, let's take a look at the poem. So let's have a look and run with the word frog, because that word appears just once in our poem. And yes, how public like a frog. Okay, cool. Let's try another one which is returns, which appears in multiple locations, which is body. Yeah, awesome. And now let's try one that doesn't appear at all, which is going to be X, Y, Z, and nothing. Cool. So this seems to be working. It works when we pass in a string that appears once, it returns that one line. It works when we pass in a string that appears multiple lines, and it works when we pass in a string that doesn't appear at all. Moreover, of course, it will work if we pass in a file that doesn't exist, or we don't pass in enough parameters. We get the appropriate error. So cool, our program is working. Okay, so we got a test here to work with case insensitive type searches. I've put that in here already, and I've also copied in the solution for the function that will search with case insensitive searches. And this works by calling to lowercase on each of the lines that it iterates through. So if we run cargo test to see if that passes, then we can see that the insensitive, case insensitive, and sensitive searches both work. So given that we've got both of these searches working in the library, we can now implement that in our run function and determine whether or not we want to use case insensitive search based on an environment variable. So if we scroll down, we can see that after we implement the function and we run the tests, we need to update our config to add a new attribute to that config. So let's go over and do that. So that's the first thing. And the next thing we want to do is update the run function such that it will ignore if ignore case is set, because ignore case is a boolean in the config, then it will use the case insensitive version of the search. So let's copy that in and paste that in here. Other than that, I think we're good in terms of the logic here. But the one thing that we need to do still is determine how to set ignore case in the config, which of course is done here. So scrolling down, we can see that the config build function is updated by adding a new library there. So we'll just add that to the top. This is for environment variables. And then in the build function itself, we add this line to set the ignore case, and we add it to our returned config object. So let's just replace that with that, and we should be good to go. Now, so this is a new environment variable which we need to include on our command line when we run the application. So if we scroll down now, we can check if we're able to run the program. So we'll just check that out here, and we can see that it's working. And now we should be able to run it with the ignore case environment variable and try that again. And now you can see that it's actually working, and it's working by calling the case insensitive version of this function. As you can see here, in this version, it's only finding cases where the lowercase 2 is found. Here, in this case, because we've used ignore case equals 1, it's also finding these 2 lines here. So the final exercise of this course here, where we're building our mini grep program in Rust, is to write error message to the standard error instead of the standard output. So if we're using print line or print lin macro, it's only capable of printing to the standard output. So we have to use something else to print a standard error. So firstly, let's confirm that the standard output is being used for everything in this application. By that I mean it will receive error messages as well. One easy way to do this is to basically run the application and pipe in, or basically channel out the output into another file. So we can take a look at that in the terminal window here. If I run this, we know that this is going to have an error, but notice we don't see the error on the screen. However, if I output the file using cat, you can see that the error got sent to this file. This means that the error message is being written to standard out, and what we want is it to be written to standard error. So let's fix that. So the way to fix this is to change the println macro to e-println. In other words, we just select this, put e in front of it, and now we can run our experiment again in the command line. So let's come back here and run cargo run output without any switches, and now we get the output, the error message on the terminal, and the file itself is empty. If we run this now with the expected switches, let's say we want to find 2 in the file poem, then you can see there's no errors output and there's no actual results output, because they should have been fed into the output file. So now we can see that we fixed the issue of the output. We are correctly sending errors to the standard error by using ePrint, and we're using the rest of the application is sending to standard output. So that's it. That is our application, an IO program that is using Rust